So I guess we can start. Thank you all for coming to today's seminar. The speaker is Sunghyuk Park at Harvard University. He will talk about 3D quantum trace map.
Thank you very much for the invitation and the introduction. It's a great honor and pleasure to be here. So in this talk, I want to talk about my recent joint work with my collaborator, Sam Panitch, where we've constructed a certain homomorphism. So it's a linear map whose domain is something called the skein module of a three-manifold. It's some vector space valued invariant of three manifolds, and whose codomain is something that's called the square root quantum gluing module, which is also a vector space valued invariant of a three manifold that is equipped with an ideal triangulation. This map can be thought of as giving a precise relationship between these two different quantizations. These two vector spaces individually have been known to be quantizations of SL2C character variety of a three manifold, and it's a certain variety of representations of the fundamental group of the three manifold into SL2C up to conjugation, which is of it's an important object in many different fields of mathematics, including mathematical physics and low-dimensional topology. Anyway, so I want to so the goal of this talk is to tell you what this 3D quantum trace map is, and what are some of the ideas that goes into this construction. So let me start by giving some background, since I assume that not everyone here are quantum topologists. So the skein module of a three manifold is the following. So let's say, so throughout this talk, Y is going to be an oriented three manifold, and let R be our base string. It can be taken to be either Laurent polynomial ring in one indeterminate A, or rational functions in A. So just some base string that has an indeterminate symbol A. Then its Kauffman bracket skein module, or SL2 skein module, is defined in the following way. So first we take the free R module spanned by all isotopy classes of framed unoriented links in Y. We mod out this free R module by these relations that I wrote down. They're called skein relations. So what do these relations mean? Is that whenever we have a triple of framed unoriented links in Y that looks exactly the same outside of a small ball, where inside a small ball, if the triple looks exactly like this triple, say this one, then the linear combination of the second two taken exactly in this way is identified with the first one. And likewise, whenever there's an isolated unknot, we can get rid of it and get a factor of minus a squared minus a to the minus 2. Yeah, so it's just some invariant of a three manifold expressed in terms of that can be defined in terms of links, modulus, and relations. And we're going to call the elements of this skein module skeins. Skein module is a very interesting thing to study, and people have been studying it for many decades. So here are some basic properties of the skein module. Firstly, the skein module of S3, the three sphere, is a free R module of rank 1 spanned by the empty skein. So the empty skein is just the element of the skein module represented by the empty link. Well, this means that given any link K in our three manifold Y, it can be expressed as some number in our base ring R times the empty link by using those skein relations. And this number, so which is going to be some Laurent polynomial in A, is sometimes called, this is also known as the Kauffman bracket polynomial of the link. And that's why this skein module, this version of skein module is also called the Kauffman bracket skein module. The skein module is when the three manifold is of the form a surface times an interval, so your I is an interval, say 0, 1. Then the skein module acquires an extra structure. It becomes an algebra, so it becomes a unital associative algebra because, say, if we have a surface times an interval, we can stack another copy of it, another copy of the surface times interval on top of it. And so whenever we have some link, some link in this in the first copy and another link in this second copy, then by just stacking one on top of another, we get a new link in the surface times interval. This gives a unital associative algebra structure on the skein module. So in this case, it's an algebra, and it's called the skein algebra of the surface. And basically by the same reason, but since we can stack a surface times interval, whenever we have our three manifold Y has a boundary component, say sigma, then the skein module of Y is a module over the skein algebra of surface for the same reason. Yeah, so on that boundary, we can stack the boundary component times interval, and we get the same thing, so that gives a module structure. As I advertised in the beginning, in the very first slide, the skein module turns out to be very closely related to the character variety of a three manifold. Firstly, something special happens when we specialize this parameter A, capital A, to be either 1 or -1. So notice that in this skein relation, when we specialize A to be either +1 or -1, say in this first relation, if we rotate this individual picture, say 90 degrees, then the right-hand side will remain the same because A inverse will be the same. Whereas on the left-hand side, what was, say, a positive crossing will look like a negative crossing. That is, the sign of the crossing is changed. It means that when A is either +1 or -1, inside the skein module, the strands of the links are allowed to freely pass through each other, meaning there is a natural commutative algebra structure in this limit, and where the product in this algebra structure is simply given by superposition of links. And because it doesn't matter how we actually superpose these, because the cosines of the links doesn't matter when we specialize A to be either +1 or -1. And in fact, when A is -1, this commutative algebra turns out to be canonically isomorphic to the coordinate ring of the SL2C character variety of the three manifold. And this was shown in the work by Bullock, Perchitsky, and Sikora in late 1990s. So these SL2 character variety is a
excuse me. What is the low gamma?
Sorry, can you speak a little louder?
What is low gamma? Gamma goes to.
Oh yeah. Rho and gamma.
Yeah, low gamma.
Yeah, sorry. I was gonna talk. Okay. So firstly, the SL2C character variety is the this space of characters of pi1 of y into SL2C, right, modulo conjugation by SL2C. And this isomorphism is given by this formula. So as I said, in once we specialize this variable A to be -1, the skein module is commuted algebra and its elements, which can be represented by some links, or some linear combination of links. Since the actual embedding of the link, since the skein module in this specialization doesn't see the crossing, we can really think of them as free homotopy classes of loops. Modulo orientation reversal. So here gamma just means here gamma is a free homotopy class in Y. Yeah, it's a free homotopy class of loop in Y. And rho is some, say, SL2C character, an element of a SL2C character variety. So it's a homomorphism from pi1 of Y to SL2C. And once we have this homomorphism, we can evaluate the holonomy along gamma, and then take the trace, this map turns out to respect the skein relation. And
can you explain one more? What is the why gamma is the element of pi1 y?
Sorry, could you please speak a little bit louder?
Can you explain one more? What is gamma? Is an element of fundamental.
Oh yeah. Gamma is it's an element of a free homotopy class of loops. So say it's a conjugacy class of elements of pi1 of y.
Thank you. So skein module in this sense gives a quantization of the character variety.
And yeah, and that's one of the reasons people care about skein modules. Lastly, okay, even though I won't need this at all in this talk, pretty recently, Gunningham, Jordan, and Safronoff showed an intriguing property of the skein module, which was originally conjectured by Witten, which is that for a closed three-manifold, the skein module turns out to be a finite dimensional vector space over the field of rational functions in A for generic
Excuse me.
value. Yeah.
So how about the A equal plus one? What happened?
Oh, you mean in this previous bullet point?
Yeah, A equal plus one case.
Yeah. Thanks for the question. Yeah, in A, when A is plus one, that commutative algebra also turns out to be isomorphic to the coordinate ring of the character variety, but not canonically so. It's isomorphism depends on the choice of a spin structure of Y, if I remember correctly.
Still same as the board ring character variety. Okay.
Sorry. Did I answer your question?
So what's the difference between A equal 1 and minus 1? So
what's the difference between A equals 1 and minus 1? Was that the question?
Skein minus 1y and skein plus 1y. Sorry. So you showed, right? Skein minus 1y is isomorphic to the positive of character variety. But how the SK plus 1y is isomorphic to what?
Yeah, it's if I remember correctly, it's isomorphic to the same coordinate ring, but that isomorphism depends on the choice of a spin structure.
Isomorphism, that is different. Okay, thank you.
Yeah, it's a non-canonically isomorphic. Yeah, so skein module, it's a finite dimensional vector space, which is actually quite surprising since this is far from being finite dimensional when A is non-generic, say minus 1, for instance. In a lot of ways, skein modules behave like TQFT in a sense that we can study skein modules more locally by cutting the three-manifold into simpler pieces. So the a relative version of skein module, that is a skein module where we look at skeins relative to the boundary, that's known as stated skein modules. Which basically first appeared in this work by Bonahan and Wang, who introduced the two-dimensional version of quantum trace map, a very influential paper. And then this notion of stated skein modules was put more formally by Tanglei, and then its properties, focusing on the case of surfaces, was studied by Cosentino and Ley. We're going to use a slightly generalized definition, which is going to be crucial later. So again, let Y be an oriented three-manifold. And we're going to put in some extra structure or data to the boundary of Y. So we're gonna draw some draw an oriented bipartite graph, some embedded oriented bipartite graph gamma on the boundary Y, and it should be oriented in such a way that the edges should be oriented in such a way that each of the vertex of gamma should be either a source or a sink. So a source is a vertex where all the edges adjacent to it are oriented away from the vertex, and the sink is the opposite one. So yeah, this picture is just a cartoon picture. It's an example of gamma. And such gammas will be called boundary markings of Y. So in previous works, people have, as far as I know, people have considered boundary markings which are disjoint unions of intervals, and we're slightly generalizing that to allow such a graph structure. A stated tangle in this pair Y and a boundary marking gamma is an unoriented ribbon tangle. So it's basically just the same thing as framed unoriented link that we were using previously to define the skein module, except that now that it's not a link, it's a tangle, meaning it can have ends. But the endpoints must lie in on the boundary marking gamma. More precisely, we require that the endpoints of our tangle to lie in the interior of the edges of the of gamma. That is, it should be away from the vertices. And moreover, to each endpoint, the stated tangle is also equipped with a function that assigns a sign, either plus or minus, to each endpoint of the tangle. So yeah, so each endpoint of a stated tangle, say this is an end of a tangle L, then yeah, firstly it should lie in the boundary marking like this, and the framing should match. The framing should be tangential to the graph, and it's assigned. It's equipped with a sign here, which I denoted by mu. Okay. Now, okay, to define this, we need to slightly enlarge our base string. Now we're gonna have to use square root of a and also square root. Oh, sorry. It should be plus minus. Yeah, square root of minus a squared. Anyway, the stated skein module of this pair Y and gamma is defined as basically in the same way as we define the skein module. It's if we first take the free R module spanned by isotopy classes of stated tangles in this boundary marked through manifold, and we mod out by stated skein relations. And the relations that we mod out by are given in this slide. So the first two are the same relations that we had in the ordinary skein module. And we have two more skein relations. The last one is is more cosmetic, and we don't necessarily need this last one, but just simplifies and it makes expressions more symmetric. Yeah, so let me just let me explain this last one first. So remember that we have a ribbon tangle, and actually I'm not going to distinguish the two sides of the ribbon, meaning I'm going to allow half twists. And so whenever we see we have a half twist in a ribbon, like something like in this left-hand side of this picture, then we can get rid of the half twist and get an extra factor, which is the square root of minus a cubed. But what's more important is this are these two relations in the middle. The first relation tells us that whenever we have a C-shaped angle that is localized like around some point on the boundary, then we can get rid of it. We can get rid of that C-shaped angle. Basically, we can evaluate it to a number, and the number is given by this. So it's going to be 0 if mu and nu have the same sign. And when they have different signs, it's going to be minus a squared to the power either plus 1/2 or minus 1/2, determined by the sign of mu. The next relation allows us to collide a part of our link to the boundary marking. So yeah, on the left-hand side, we have a part of our link. We can pull it, collide it to the boundary, and open up that strand like this. And then we get this linear combination of two stated tangles given in this way. So at this point, it might seem like just a random set of relations to you, but it'll turn out that these are natural relations to impose, and in particular, I'll highlight some of the properties of the stated skein models. Any questions so far? Just like in the case of skein modules, when our three-manifold is a surface times interval, then it requires an algebra structure. So in particular, if sigma is an oriented surface whose boundary consists of intervals, so something like an n-gon, say this is an example of a hexagon. So it's a disk with 6 punctures on the boundary. So the boundary consists of 6 intervals. Then we can just choose a set of marked points consisting of 1 point from each boundary interval, something like this. And then we cross-fit interval, we cross-fit I, and we orient all the, and then those marked points on the boundary, they become intervals. We orient them all, say, in one direction. Then this is a boundary marked three-manifold, so we can define the stated skein module. And by the same reason as before, that we can stack this, stack 2 of these, 2 copies of, say, this hexagonal prism on top of each other to get the same hexagonal prism. This stacking gives an algebra structure. And this is called the stated skein algebra. I'm abusing notation. I'm using the same symbol for stated skein algebras, but basically throughout the talk, unless stated otherwise, I'm only gonna be talking about stated skein modules and stated skein algebras. So whenever I wrote the symbol sk or sk-alg, you should think of them as skein algebras, stated skein algebras and stated skein modules. Okay, so now let me explain why why it's a good idea to generalize, why it's a good idea to allow vertices like these. Why it's a good idea to allow vertices to the boundary marking. So I mean, it's a pretty simple observation, but it's also a crucial observation, which is that let's say V is a vertex of a boundary marking. It's going to have some degree. In this picture on the left, it has degree 3. Then we can say first remove that vertex, remove a small neighborhood of the vertex, and then that's topologically the same as, so we can pull this vertex, we can pull a triangular prism out of the vertex like this picture on the right. And then if we look at this part of this picture, it looks exactly like a triangular prism, meaning it's module. It's a module over. It's going to have a module structure. It's going to be a module over the stated skein algebra. In this example of a triangle, D3, because the stated skein algebras of a triangle consist of stated skeins in this triangular prism with this particular boundary marking, and so we can stack this whenever we have a stated skein, something like this. We can stack this on top of this picture. That gives a module structure, basically inserting the corresponding tangle. So in this example, so in our convention, left multiplication corresponds to stacking on top if the boundary markings were all oriented upward. So this is a left module structure. And that was for us when the vertex was a sink. Likewise, when the vertex were a source, that is, if the all the adjacent edges were oriented the opposite way, it would have a right module structure. So combining everything.
Excuse me.
Yeah.
What is D? D.
Oh, what is D sub degree? What is the n? Yeah. Sorry, I should have said it carefully. So yeah, that's by that I mean an n-gon, which is a disk with n punctures on the boundary. So yeah, this example is like D6 is a hexagon. Yeah, D3 is a triangle, etc. Thanks for the question.
Yes, yeah.
Yeah, so combining everything, well, I just said, this stated skein module of a boundary marked 3-manifold Y, comma, gamma it's a bimodule over, so firstly, it's a left module over tensor products of stated skein algebras of polygons, one for each sinc vertex. And it's a right module over the same thing, tensored over source vertices. So so a stated skein module is not just a vector space. It has some rich structure in it, and it's going to be crucial to use this structure.
I have a question.
Oh, yes, go ahead.
For the internal vertex of this graph, do you allow the valence to be 2?
Yes. In that case, it would be a module over a skein algebra of a bigon.
Okay.
Yeah, skein on. Yeah, it could be. Yeah, it could be 1. It could be 2. It doesn't matter.
Okay. Thank you.
Okay. Yeah, this is just a side remark. Like one way to think of this module structure is as something that gives a skein relation where under sliding an endpoint of our stated tangle across a vertex of a boundary marking. So let's say this is part of our stated tangle. So it has an end point on this boundary marking, and say it has state mu, and it's close to this vertex over here. And so in the definition that in the definition of the stated skein module I gave, we're not allowed to slide this endpoint across this vertex. But what one can do is that instead of sliding it, we can kind of pull this strand and collide it to this adjacent interval. This another edge of the boundary marking. So basically breaking up the stated skein in this way. So it's a linear combination of stated skeins. I mean, we're just applying one of the stated skein relations in the definition of the stated skein module. But the point is, once we have broken this up, then this part of the stated skein can be thought of as an action. So this part is thought of as an element of the stated skein algebra of some polygon. Let's say this has degree. This vertex has. Let's say this vertex has degree n. Then we can think of this as an action by an element of a stated skein algebra of an n-gon to this stated skein. So in other words, when we slide an endpoint of our angle across a vertex, we get a skein relation with coefficients in those stated skein algebras of the vertex. So this is one way of thinking about these, like what these module structures are doing. Yeah, so as I said, this bimodule structure will play an important role later. But for now, let me review the story in 2D first. Okay. Yeah, this theorem really justifies like why why stated skein modules and algebras are a natural thing to study. So Tong Lei and Cosentino and Lei, they've shown the following. So they were studying stated skein algebras of surfaces, and let's say C is an ideal arc, meaning it's an arc in the surface sigma, whose endpoints are both punctures on the boundary. Okay, sorry, the puncture doesn't have to be on the boundary, but it's an arc whose both ends are punctures. Then we can cut the surface sigma along this ideal arc, creating a new surface that I denoted by sigma prime. So this cutting is depicted in this figure over here. And then the theorem is that then there is an algebra homomorphism called the splitting homomorphism from the stated skein algebra of sigma to that of sigma prime. And this map is defined in a natural way. So for any stated tangle L in sigma times an interval, it is mapped to, so that's yeah, let me say, let me draw, yeah, let's say this is part of L, then that gets mapped to so L prime, yeah, L prime is denotes the tangle obtained by cutting L along this ideal arc times interval. And it's going to have some newly created ends, and we have to sum over all ways of assigning states to the boundary. That's what I mean by this summing over all the epsilons, which are functions from L intersect C to plus minus. So I don't know, let's say we assign states epsilon 1, epsilon 2. Yeah. And then we sum over all possible ways of assigning states, and that's the map. And so and saying that this is an algebra homomorphism is a claim that this is a well-defined map, meaning it's invariant under isotopies or applying skein relations of L. Yeah, and the existence of a splitting homomorphism allows us to study allows us to study skein algebra of surfaces by cutting it into simpler pieces. And this, I think this is a very powerful idea. Just wanted to mention a few properties of stated skein algebras of surfaces. So let's say our surface is a bigon, so it's a disk with two punctures on the boundary. Then there is an ideal arc connecting the two punctures, and once we split, we get two bigons. And well, this splitting map endows this stated skein algebra of bigon a coalgebra structure. The splitting map becomes a co-product map. And it turns out that this stated skein algebra is in fact a Hopf algebra, and so as Hopf algebra is isomorphic to this OQ of SL2, so a quantized coordinate ring of SL2, which is a Hopf dual of the UQ-SL2, the universal quantized universal enveloping algebra of SL2. Yeah, so this is something shown in Cosentino Lei, and I think it's a really nice like way of thinking about the quantum groups, the quantum group in terms of like more concrete, more kind of geometric objects like tangles. Okay, so we got interesting algebras out of stated skein algebras. Moreover, for each boundary interval of the surface sigma, we can say we take this boundary interval, we can cut along an ideal arc that is very close to the boundary interval, but by connecting the two punctures, so we can split off a bigone like that. And yeah, that gives the stated skein algebra of the surface sigma a co-module structure over the co-algebra, which is the stated skein algebra of a bigone.
Oh, excuse me.
Yeah.
So here, skein algebra sigma is the relative one, or
Oh yeah, sorry, yeah. So every time in this talk, when I say skein algebra or skein module, it's unless stated otherwise, it's gonna be the relative version. It's gonna be the stated skein. Yeah.
sorry, relative one, or what?
Yeah, it's gonna be the stated skein modules, like which is the relative version, which is the one spanned by the tangles rather than links.
Sorry, I could not understand. So you define two different skein algebra of three manifolds, right? One is the absolute one, another one is still
yeah.
the
So
boundary, right?
yeah. So these are the skein. These are the older definition of stated skein models and skein algebras, where those are spanned by links inside the three manifold. But since we want to be able to like study skein models and skein algebras by cutting it into pieces, but the problem of just using this naive definition of skein models and skein algebras is that like, when we cut a three manifold, the link inside it is also going to be cut into pieces. So we can't just work with links. It kind of forces us to study tangles ending on some boundaries, ending on the boundary of a three manifold. And that's why these people have introduced this notion of stated skein module, which is a relative version, which is a version of skein module relative to the boundary, which is spanned by tangles, or more precisely, stated tangles. It's spanned by tangles, but its endpoints also carry state, which is a sign, which is an assignment of a sign, either plus or minus, to the endpoints. Yeah, and yeah, so in this talk, unless otherwise stated, I'm only going to be talking about the stated skein modules and algebras.
Okay, thank you. Yeah, thank you.
Right. Right. So we have a co-module structure for each boundary interval. Moreover, Constantine and Lay, they've also shown that. Okay, so in the previous statement on this splitting map, once we've split into to sigma prime, we have these two new boundaries, right? Two boundary intervals in sigma prime, and that endows the skein algebra of sigma prime by co-module structure over this co-algebra, which is the skein algebra of a bigone. Yeah, they've Constantine and Lay have shown that, in fact, the splitting map is an isomorphism onto the zeroth Hochschild cohomology of this bicomodule, which is a submodule of which is a subspace of this skein algebra of sigma prime. Okay. Yeah, I feel like I'm going a little too slow. But let's see.
You can go over time
Okay.
if it's fine for you.
Yeah. Okay. Okay, so I've just reviewed the notion of stated skein module and some basic properties of stated skein algebras. And this next thing I want to briefly talk about is a certain nice quotients of stated skein modules and algebras called reduced skein modules and skein algebras. So, you know, even though the stated skein modules and skein algebras are defined in a pretty simple way in terms of the generators and relations, it may not always be easy to study their like algebra structure explicitly. But it turns out that if we take a quotient of these modules, by killing certain arcs, certain elements called bed arcs, then very often these skein algebras and skein models, that their structure becomes much simpler, so they're easier to study. Yeah. So, what are bed arcs? So we say that a stated tangle in boundary marks 3 manifold y comma gamma of the following form. So imagine that these are pictures seen from outside of y. Say imagine we're standing outside of a 3 manifold y. We look at its boundary, and on the boundary, it has this boundary marking drawn in these orange lines. And just below the boundary, there are these tangles with these specified states. And the tangles of these forms are called bad arcs. Likewise, when our 3 manifold is a surface times an interval, then tangles of this form are called bed arcs. And this is a notion, I think, introduced in this work by Constantine and Le. And we're gonna kill these elements.
Can I ask a question?
Yeah.
Are you viewing this bad arc for surface times interval as an example of the above one?
Well, yes, but maybe I can explain a little further. So really to think of it as an example of this first one, okay, let me draw an example of, say, a triangle. So this in case of this triangle, we have this triangular prism with this boundary marking. But to match with this definition of the first, really, we have to kind of take a cone on the top and the bottom. So basically, kind of close off this boundary marking to create a sink on the top and a source on the bottom. Or maybe let me draw a slightly different. Oh yeah, I think with this one. Yeah, and then this definition on top is the same as this. Yeah, then this definition for yeah, and this in case of surface times interval, those are exactly the boundaries. So those are, say, for example, arcs going plus minus. Like if we pull this to the top, that looks exactly like this one. If we pull it to the bottom, it looks exactly like this one.
Okay, thank you.
Yeah, and but by the way, just let me just comment that this taking a tone on top and the bottom. So I've remarked earlier that this we have module structures for each vertices of the boundary marking. So say at this point we have a left module structure of over, in this case, of a skein algebra triangle, and we have a right module structure of a skein algebra of triangle on the bottom. And yeah, in this case, it's really just a skein algebra of a triangle itself as a left regular and right regular module over itself. That's just what it is. Okay, so the reduced skein algebra, which we'll denote by SK-alg with an overline, it's a quotient of the stated skein algebra of a surface by the two-sided ideal generated by those arcs. And yeah, we define it similarly for reduced skein modules. Yeah, it's a quotient of the ordinary stated skein modules by those bad arcs. Here's a proposition which says that the reduced skein algebras of a bigon and a triangle have particularly simple structure. So the reduced skein algebra of a bigon is nothing but a Laurent polynomial ring in one variable, say x, where stated skeins like this is mapped to x, and stated skeins with like minus signs, minus gets mapped to x inverse. The ones with either plus minus or minus plus, those are all killed because those are bad arcs. And for later use, I'm gonna call the reduced skein algebra of a bigon by this math BBB, and sometimes I call it biangle algebra. In case of a triangle, the reduced skein algebra of triangle, it's not commutative, but it becomes almost commutative. So it's a quantum torus. It's an algebra of Laurent polynomials in A commuting variables, meaning it's generated by these alpha, beta, and gamma and their inverses, where alpha and beta commute up to this capital A, gamma and beta also commute up to capital A, and likewise for alpha and gamma. And in terms of stated skeins, these alpha, beta, and gamma correspond to these stated skeins around each vertices. Yeah, this fact that once we have killed all the bad arcs, then these reduced skein algebra becomes almost commutative will be used later. I think it's an important ingredient in both the construction of a 2D and 3D quantum tracement. So here I'm building up to explain what the construction of the two-dimensional quantum trace map is, which was the work by Bonohan and Wang, and also described in terms of status skein algebras by Cosington and Ley. But here, we need one extra step in that construction, which is so we have this triangle algebra, was denoted by map PVT. We have this triangle algebra, but we're going to embed it into a slightly bigger quantum torus that I call extended triangle algebra. So if I label, say we have a triangle, if I label the vertices by alpha, beta, and gamma, and the edges by A, B, and C, then then I'm going to think of these variables as associated to the vertices and edges. Then there's a natural embedding of the triangle algebra to the extended triangle algebra by this map. Here, the square brackets means the Weyl ordered product. It's a way of taking products in a quantum torus that doesn't depend on the choice of ordering of variables. And yeah, so we have this algebra embedding, and so putting these together, so we start from the reduced skein algebra of a surface. We apply the splitting map. Let's say we have chosen an ideal triangulation of the surface. We cut it into ideal triangles. Then it would map to the tensor product of reduced skein algebras of triangles, which I called the triangle algebras. So this map, one for each face or the triangle of the triangulation. And then we can just use this embedding I just mentioned to embed it into a slightly larger quantum torus. So this is an algebra homomorphism from the skein algebra or reduced skein algebra of surface to some quantum torus. The image of this composition turns out to lie in something called square root Chekhov-Fock algebra. Okay. It's going to take much longer to explain what quantum Teichmüller space or the Chekhov-Fock algebras are, so I didn't plan to talk about it in detail. But basically, there are two well-known quantizations of character variety of surfaces. One was the skein algebra of surface. There's also another one that I didn't explain, which is a quantum Teichmüller space that it has coordinate charts, each depend on a choice of triangulation. In each chart, it looks like a quantum torus called Chekhov-Fock algebra, and so this composition is a map that relates the skein algebra of surface and the quantum Teichmüller space. And this is the map. This was the map constructed by Bonohan and Wang in their work. Yeah, and what we're trying to do, or what we did in our paper, is to generalize this to 3D. Okay. So yeah, we're gonna generalize this to 3D. And a three-dimensional analog of quantum Teichmüller space is something called the quantum gluing module, which I wouldn't have time to explain in full details, but roughly, if you're familiar with three-dimensional hyperbolic geometry, then there are these coordinates called shape parameters, often denoted by z, z prime, and z double prime. These are certain complex valued numbers associated to, so let's say we have a three-manifold Y, which has ideal triangulation. And for each ideal tetrahedron, we associate these variables to the edges. These are roughly complexified and exponentiated dihedral angles. You can think of it that way. They must satisfy a set of, once they satisfy a set of equations, then that describes a complete hyperbolic structure, or more generally, some PSL2C flat connection on the three-manifold. And it turns out that they can be quantized. These coordinates can be quantized, called quantized shape parameters. So now these are Q commuting variables. These are variables commuting up to some scalar, and they must also satisfy the quantum version of the relations that are satisfied by the usual shape parameters. So yeah, in analogy with this two-dimensional quantum trace map, we would like to construct a homomorphism from the skein module to the quantum gluing module, or more precisely, it's like slight extension of it that includes square roots of these parameters. One ingredient, we need to introduce a notion of combinatorially foliated surfaces. So this is just the kind of surface that behave nicely. So we want an analog of the splitting homomorphism, and so we want to split a three-manifold along some surface. And when we split, then we'll have to introduce some boundary marking to the newly created surfaces, and a structure of combinatorial foliation kind of gives a natural way of putting a boundary marking to that surface. So simply put, it's just a decomposition of a surface. The combinatorial foliation is a decomposition of the surface into pieces that look like this. So these are, so this is a quadrilateral with, say, two punctures in two opposite vertices, and we also put a diagonal marking connecting the other two vertices. And we also require that when these quadrilaterals are glued together, the orange vertices, once it's a source, it should remain a source. Once it's a sink, it should remain a sink, and so on. That is, only sources are glued to sources, sinks are glued to sinks. And it's probably easier to see examples, right? So yeah, to understand what it means, what I mean by that. So these are some examples of combinatorially foliated surfaces. These are just some surfaces, and very simple examples of combinatorially foliated surfaces, which can be obtained by gluing a bunch of these quadrilaterals. And by the way, we call these combinatorial foliation because really our inspiration was actually once we have such a decomposition of surface, then we can associated topological one-dimensional foliation, like these black lines I drew. And which you can also think of as giving a strong deformation retract of this quadrilateral to this marking. And yeah, that's something and that's something inspired from from something called spectral networks. Yeah, I'm not going to get into details, but anyway, combinatorially foliated surfaces are the type of surfaces that we're going to use when we split our three manifold. Okay. So yeah, it's a long, yeah, it's pretty long to state, but just to give you an idea, the basic setup is the following. So we have a three manifold Y. We split it along some surface, sigma, which is combinatorially foliated. And once it's combinatorially foliated, it has some natural it has natural boundary marking. Let me draw it this way, just an example. And so, and let's say the resulting three manifold on two sides are, let me call them Y1 and Y2. They may be manifolds, three manifolds with corners and stuff, so the boundary markings may extend like this, or these Y1 and Y2, they might have some boundary markings that that already exist in Y. The point of this theorem is that there is an analog of a splitting homomorphism in this setting. That is, once we have such a setting and given any state tangle L, we can map that to, we can basically use the same map. We can map that to the sum over all states that we can assign to the newly created boundary. But there's a twist, which is that in order for this map to make sense, we actually need to impose some extra relations. So this codomain I wrote here is not the ordinary tensor product of SR modules, but rather something like we call the reduced tensor product or relative tensor product, which is a certain quotient of this tensor product SR. Yeah.
Excuse me.
Yeah.
Excuse me. The skein Y gamma, right? Y has no boundary, right?
Y can have boundaries and such, etc. Yeah.
Y can have a boundary.
Yeah. So yeah, Y can have boundaries, and yeah. So here, yeah, what I drew here, these are part of boundaries of Y right there.
I see. Y still have the boundary, and gamma is on the boundary of Y, right?
Yeah. Gamma is a boundary marking of Y. But as we split Y along sigma, it now creates more boundary marking given by the combinatorial foliation of the surface.
Okay. Thank you.
Right. Yeah. So the codomain is not the usual tensor product as R modules, but rather it's a quotient of it. by the relations, which is that if this is our combinatorially foliated surface sigma, and let's say this is a vertex of marking on that combinatorially foliated surface, then we know that by the observation that I made earlier. Okay, so we have this, all right, y1, y2, this was sigma. Then there's going to be a copy of this boundary marking on this y1, boundary of y1, boundary of y2, right? And we know that the vertices of a boundary marking gives a module structure. So the skein module of y1 comma gamma 1 will have a module structure over the polygon, over the n-gon, where n is the degree of this vertex B. And same for skein module y2 comma gamma 2. And morally speaking, what I wrote here really just says that when we take the tensor products, we need to take a tensor product over algebra, over kind of like how when we take the tensor product of a left, when we take the tensor product of a right module and a left module over the same algebra, that's different from the ordinary just tensor product as vector spaces, where imposing some relations, like some compatibility relations, like action of the algebra to the left and to the right are the same, right? And this is basically that kind of relation that we're imposing. So, which is natural thing. When we so under the splitting map, the codomain is not the ordinary tensor product as R algebras, as R modules, but rather it's a tensor product as it's a relative tensor product as modules. So here we're really crucially using the module structure. So we have this splitting map. So we're gonna apply the splitting map to an ideally triangulated three manifold. A natural way of splitting an ideally triangulated three manifold is to split it into ideal tetrahedra, obviously. But it turns out that a better way, or a more natural way to split a three manifold is into a slightly different pieces that we call phase suspensions. So what do you mean by a phase suspension? For each face F of an ideal triangulation, of a suspension that we denote by SF, just a suspension of a face, is this blue piece. So yeah, it's a join of that face with the two barycenters of the two adjacent tetrahedra. And for each phase suspension, this is the associated boundary marking that we'll be using. And note that this boundary of phase suspension is a combinatorially foliated surface. And in particular, it has two sinks of degree 3. And it has 3 sources of degree 2, meaning the skein module of the phase suspension is a bimodule. It's the left module of over 2 copies of triangle skein algebra of triangles, and right module of 3 copies of biangles skein algebras. Bimodule. For later use, let me introduce 2 more terminologies. So the faces of the phase suspension, for example, this face, these will be called sometimes we call these edge cones, or the cone over edge, in a sense that it's really a cone over this edge with respect to this top bare center. We also use the terminology to talk about the edges. So this edge, for instance, this one that I just drew by purple, we call this vertex cone. It's a cone over this vertex with respect to the upper bare center. So these are what phase suspensions are. And so given an ideal triangulation of a 3-manifold, we can split it up into phase suspensions rather than into ideal tetrahedra. So the corollary of this of the splitting map that we have, that I showed you earlier, is that there's splitting map. Here I'm just using the reduced version because this is what we're gonna be using in the end anyways. So the corollary is that there's a natural homomorphism from the reduced skein module of Y to some quotient of the tensor product of reduced skein modules of phase suspensions, one for each face of the ideal triangulation. And this quotient we're taking are exactly the following relations. So for each edge of a triangulation, let's say this is an edge, then this edge, there are going to be some number of tetrahedra that shares the edge, like this. And likewise, there's going to be some number of phase suspensions that shares that edge. Then that edge is going to be, if we look at the corresponding boundary marking, it's going to have some number of that edge is going to contain a vertex. The midpoint of the edge is going to be a source vertex of degree 2. So that's where I drew these figures. And yeah, and we have this relation that insertion of little tangles around each of those, basically by the action of a biangle algebra, is the same as just multiplication by an overall scalar. And likewise, for each vertex cone, there are going to be 3 phase suspensions that shares that vertex cone, and these are the relations that we have to impose. And so these are relations among the left actions of tensor products of triangle algebras. In case you're familiar with the relations satisfied by the shape parameters, you might notice already at this point that this first relation is the analog of the gluing relation. The second relation is the analog of the vertex relation, the relation that the product of z prime, z double prime is -1. This last relation is the Lagrangian relation, which says that z prime is 1 minus z inverse. Yeah. We also have a structure theorem that basically characterizes what skein modules of a 3-ball whose boundary is combinatorially foliated. So those skein modules are cyclic modules over the bimodal structure. It's spanned by the empty link. And all the relations are generated by certain relations of this form. But as a corollary, we obtain a very explicit presentation of the reduced skein module of the phase suspension. So remember that T's are the triangle algebras, these are the biangle algebras, and yeah, so it's a bimodule, as I pointed out earlier, and it's given by its relations are generated by these three explicit relations. Remember that in the setup of 2D quantum trace map, we had to use an embedding of the triangle algebra to a bigger triangle algebra. That was one of the ingredients, and we have the exact analog of that, which is that this reduced skein module of phase suspension embeds into tensor product of 2 copies of the extended triangle algebra, and this is a bimodule embedding. And the embedding is simply given by just mapping the empty skein to 1. Yeah. Yeah, now we're almost done. Now we can put everything together, what I've said so far. So let's say Y is a 3-manifold, Y is ideally triangulated 3-manifold, something like, I don't know, the complement of a hyperbolic knot, say. Yeah, then we have a splitting map that maps this reduced skein module to this reduced or relative tensor product of reduced skein modules of phase suspensions, and which was a quotient of the ordinary tensor product. And we had to impose some set of relations that looked like gluing relations, vertex equations, and Lagrangian equations. And yeah, I just mentioned that there is an embedding of this, there's a bimodule embedding of this skein module to some quantum torus. This is this top arrow. But we have to impose some relations to pass to the quotient. And a natural thing to do is to basically take a quotient of this quantum torus by the images of the relations that we have to impose when we take this quotient. That is, we can take the maximal quotient here. That's what we denote like this. So this is some left and right quotient of a quantum torus. And this composition is exactly what we constructed. This is a 3D quantum trace map. Yeah, so and what we're doing is like very much analogous to what other people did in 2D setup, but of course, like with some new ideas. And like what's quite what's nice about this is that, like, as I just mentioned in passing, that these relations that we have to impose when we take the tensor product, they really do become the relations satisfied by the quantized shape parameters in the quantum gluing module. So so the 3D quantum trace map is really a map from this skein module of a 3-manifold to a submodule of this quotient of a quantum torus, which is what we call a square root quantum gluing module, which consists of Laurent polynomials and square roots of quantized shape parameters. Yeah, so that's what we show, what we construct in this paper. So yeah, this last slide. So just to summarize, we generalized the notion of status skein modules by allowing the boundary markings to be bipartite graphs, and we observed that it has a natural bimodal structure. We introduced the notion of combinatorial foliation and showed the existence of splitting homomorphisms for the skein modules of 3-manifolds, like when we split a 3-manifold along combinatorially foliated surfaces. And then I also mentioned that there's a structure theorem for skein modules of 3 balls, and use it to construct the quantum trace map for phase suspension, which was this bimodal embedding of a reduced skein module of a phase suspension to some quantum torus. And then, yeah, eventually we could put everything together to construct a map from the skein module to the square root quantum gluing module. Okay. I apologize for going very fast in the last, I don't know, 10 minutes or so, but thanks for your attention, and I'm happy to answer any questions.
Thank you. So let me pause recording first.